Welcome to Fisher Control's video training program. We hope you find the information in this course helps you to perform your job more efficiently and with greater understanding. This videotape presentation has been developed in coordination with a corresponding student guide entitled P&ID and Cascade Control. Whether you read the entire student guide before watching this tape or read it section by section as you progress through the tape, it is a good idea to follow along with the guide as you view this presentation. This is the fourth of 5 units dealing with the study of fundamentals of process control. This is an introductory course designed to familiarize you with the rationale, terminology, and techniques involved in the control of various types of industrial processes. As we have learned in earlier units of this course, when we talk about process control, we are describing both the process and its control system acting as a single unit to keep the process output stabilized at its set point. There are 2 methods of process control that are commonly used to do this: open loop and closed loop control. Open loop control manipulates a process input or inputs without measurement of the actual controlled variable. This means that there is no assurance that the changes made in the inputs will result in the desired changes in output. For this reason, the closed-loop method of process control is much more common throughout industry. Closed-loop control generally means that the process output or controlled variable is measured and then, by means of a feedback loop, is used to form the basis of calculations within a controller to determine the change in input necessary to keep the process within its desired operating parameters. The most commonly used controller is the conventional 3-mode or P&ID controller. P&ID is an acronym for proportional, integral, derivative, the 3 operating modes of the device. Control loops that operate through the use of a P&ID controller have become the basic building block of planning process control strategies. There is a good reason for this. The P&ID control algorithms contain every element that is important in the feedback control of a process variable. The proportional mode deals with the process error as it occurs, or in other words, with the change itself. Integral action deals not only with the magnitude of the error, but also with its duration, and the derivative mode adds a final control dimension by considering the speed at which the change is happening. In the second half of this unit, we will look at a control strategy used when a process is really 2 processes in series, functioning as a unit. This strategy, which is called Cascade Control, involves the use of a feedback loop within a feedback loop and can result in improved performance of the overall process. Cascade control is sometimes used as an alternative to feed-forward control, which will be discussed in the next unit. Before we get into our discussion of the individual and combined operating modes of P&ID controllers, let's briefly consider a few terms that we'll be using throughout this unit. Controller tuning is the procedure through which various operating levels are set in order to make the loop perform in a stable manner and still be responsive to change. Process stability means that the controlled variable will stay at a certain value rather than cycling around. As we will see, you can make a loop very stable by tuning it very low, but in so doing, you will tune out its ability to respond to change, which is why it is there in the first place. Conversely, if the loop is tuned too high, you can kiss stability goodbye since the controller will be calling for changes that are more drastic than the process can possibly accommodate. The achieving of the proper balance between stability and responsiveness is the art of good tuning. As we have already mentioned, P&ID stands for proportional, integral, and derivative. These terms are used interchangeably with proportional band, reset, and rate. Most of the control situations we will discuss in this unit are executed automatically as a part of a closed loop with feedback. In a closed loop, the measurement sensor and transmitter provide the process input to the controller, and the operator provides the set point input. The output from the controller will be a function of both inputs and the settings for the proportional, integral, and derivative modes. If any part of the loop is broken, automatic control will not be possible. This condition is called an open loop. As you can see, the sensor and transmitter still provide the process input to the controller, and the operator continues to provide a set point input. The P&ID controller is still performing its function according to the settings on its 3 modes. However, we can't get our control signal to the valve because our loop is open. Now let's begin by discussing the concept of error. Error is a difference that exists between the desired value or set point and the actual value of the process-controlled variable. Error has 3 components: magnitude, duration, and speed of change, or rate. The measurement and feedback of error to a controller is the basis of automatic control. A P&ID controller can apply its 3 modes to measured error in various configurations involving single mode or combined mode operation. First, let's examine each operating mode individually. Proportional action provides for a controller output that is in proportion to a measured change in the magnitude of process error. This means that an error can exist, but no proportional action will be taken unless the amount of that error changes. The integral mode takes the magnitude of the error and factors or integrates it with the length of time it has existed, which is also called its duration. In the integral mode, the magnitude of the error may be constant, but there is now a periodic repeat of proportional action that will continue until there is no error left against which to apply it. The derivative function of the controller calculates how fast the magnitude of error is changing and uses this factor as a component of the control signal. This calculation is made by dividing the change in error by the time in which the change took place. Since a step change in input takes place in 0 time, this calculates as an infinite slope, which causes the derivative mode to hit the panic button and pump up controller output to the maximum. For this reason, many controllers are actually designed to consider the rate as a function of time and the change in the process variable, rather than time and the change in the error between set point and process variable. This approach eliminates the problem of a large output spike caused by a change in the set point. The output of the controller is, of course, the signal that will determine the degree to which inputs are altered in order to achieve control of the process. In a proportional-only controller, the output is a function of the change in error and the controller gain setting. For example, if the set point or input is suddenly changed by 10% and the gain setting is 2, the controller output will change by 20%, which is 10% times 2. If our controller was pneumatic and its output was 3 to 15 psi, its span would be expressed as 12 psi, and the actual output change of the controller would be 20% times 12 psi, or 2.4 psi. Similarly, if it were an electronic controller with a span of 16 milliamps, the actual output change would be 20% times 16 milliamps, or 3.2 milliamps. The term gain, whether it is applied to the output of a controller or the output of a process, is defined as the ratio of change in output to a change in input at a specified frequency, or to a given step change in input. The term proportional band is often used as another way to express gain. The two are related as shown in this formula. Proportional band, or PB, equals 100% divided by the proportional gain, K sub P. In this illustration of proportional output in an open loop, we see that the input change caused by a step change in the set point is 10%. Our proportional-only controller is operating at a proportional band setting of 50%, which is a gain setting of 2. This means that the output of the controller will be 10% times 2, or 20%. Since this is an open loop, the control signal will not affect the process variable, and even after the loop is closed, the error will continue to exist as it is until another change in its value is measured. A control loop may have many components, and the combined actions, delays, and responses of all of these devices determines a natural loop frequency, or critical frequency. This is also the frequency at which the loop will tend to oscillate. So if a closed loop is operating at its critical frequency, and you want stable performance, the important thing is to properly set the gains of the various modes of the controller. In this illustration, the proportional band is high at 200%. This is a gain setting of 0.5, and you can see that we certainly have stability. There is no cycling in either the controller output or in the process variable. However, the gain is so low that the controller only increased 5% for a set point change of 10%, and the process variable hit a new steady state considerably under its set point. Since there is no further change in error, this error will continue indefinitely. Now let's look at a reverse of the situation. High gain at the critical frequency. The proportional band is 10%, that's a gain of 10, and it's so high that when the controller sees an error of 10%, the output tries to go up 100%, which of course is through the roof. The result is that the output begins cycling, as does the process variable, which is trying to respond to these drastic oscillations in controller output. The process variable does get closer to the set point than it did with low gain, but we've still suffered a big loss of stability. Now, let's look at integral control. Again, we open the loop so that we're only looking at controller output and not the response of the process variable. We have a step change of 10% in our set point, which, with the controller gain set at 2, causes output to jump up by 20%. Because there is no further change in error, although the error still exists, in the proportional only mode, there would be no additional controller action. In the integral mode, however, the same degree of proportional action will be repeated until no error remains. So, in the example, we see that once every minute, the 20% increase in output is repeated because the error still exists. Since this is an open loop and the process variable is not being changed by this signal, we must eliminate the error by returning the set point to its original value, which is a 10% reduction. Immediately, we see a corresponding 20% reduction in the controller output, and since there is now no error, the repeat or reset of the proportional action is no longer activated. On controllers, the frequency of this repeat is expressed either in repeats per minute or its inverse, minutes per repeat. This value is called the controller reset. Looking back once more at our illustration, you should notice that even as the error is 0 and the controller output has stopped changing, it is still considerably higher than it was at the starting point. This is due to the ramping effect of the reset action. Now that we've seen what reset does to the controller output in an open loop situation, let's apply reset to a closed loop and observe the results. As we add this additional gain component to the loop, we will see that increasing the speed of the reset action will increase the speed of output change and give the loop a greater tendency to cycle. This illustration shows a proportional band setting of 80% and a slow reset of 2 repeats per minute. The step change in input was 10%, so proportional action should cause an increase in output of 12.5%. Since there is a continuing error, the proportional action is repeated until the process variable is brought up to the level of the new set point, where it gradually reaches a new steady state. However, with the reset at 6.5 repeats per minute, the proportional action is repeated too often, and the process variable is made to respond too sharply upward, so that it overshoots the set point. Now the controller must correct downward, and the same thing happens in the other direction, so that now both the controller and the process variable are chasing each other in a continuing cycle that may never settle on the set point. The third mode of a P&ID controller is the derivative, or rate mode. The controller output from the rate mode is a function of the speed of change of the error. Once more, we go to an open loop so that we can better observe the controller output response. Here, we have an error that is ramping upward. We'll assume that we have a proportional band setting of 100%, that is, a gain of 1, which means that controller output will directly track input. The rate, or derivative, is expressed in minutes, so we will choose a rate setting of 2 minutes. In that time, the controller output increased 10%, assuming that the output has a constant slope. The rate action mode makes a change in the controller output equal to this value, and it does so very quickly as soon as the slope of the change can be detected. In a proportional plus derivative controller action, the total controller output is the effect of rate plus proportional gain. Of course, if we had a higher gain setting, the slope of the proportional curve would be steeper, which would make the rate output larger as well. As we mentioned earlier, if the input were a step change, the slope of the error is almost infinite, which causes a very large output spike in the rate output. For this reason, rate mode is normally used on slow processes with largely noise-free signals, such as those involving temperature control, as demonstrated in this example. Here, we assume that the proportional band has been set at 50%. There is no reset, and at this point, there is no rate setting. With only proportional action, the set point bump of 10% causes an output increase of 20%, which is insufficient to bring the process variable to the new set point level. Since there is no further change in the error, the current error continues uncorrected. Now we add a 1-minute rate setting to go along with our 50% proportional band. Right away, we get that large controller spike that goes along with a step change in input. After several controller oscillations through the set point, it is apparent that the process variable still will not reach the new set point. Next, we increase the rate setting to 10 minutes, which has the effect of greatly increasing the total controller gain. Now we really get to see controller oscillations, and the process variable still won't come up to the new set point. From this, we can deduce that reset action will be necessary to bring the process variable to the desired level. Either fast processes with rapid changes in inputs or processes with signal noise that might appear to the controller to be an input change are poor candidates for derivative control. In selecting the proper controller mode, you must base your choice on the type of process you are controlling. Most processes respond to two-mode control, but all three are necessary to guarantee overall control of all processes. Proportional-only control is generally used to control liquid level or other non-self-regulating processes, since the process itself acts as an integrator by generating a continuing change in error. This will normally bring the process variable back to set point by causing continuous repeats of proportional action. Proportional plus integral, or PI control, is the most common type of control because the two modes combine to permit tighter control of a loop and faster response to changes or errors. P&ID control uses the combined proportional, integral, and derivative modes to control slow, low noise temperature loops. As was mentioned in the introduction to this unit, when a system may be considered as two processes in series, and each process is subject to load disturbances, control performance can be improved by an additional feedback loop. This strategy is called Cascade Control. In this portion of the unit, we will illustrate some applications of Cascade Control using examples of several common processes. Our first example diagrams the operation of a steam heater. Here, the primary objective is to control the outlet temperature. We are assuming that the inlet flow is constant. There are two loads to consider. The first is the temperature of the inlet feed, which shouldn't be too much of a problem since it will be slow in changing and should be well within the response range of our controller. The second load, which is the steam flow, could change very rapidly, causing a quick and substantial change in the steam temperature. We will also encounter a big lag as the steam heats up the pipes in the exchanger at the heart of the heating process. This significant lag in the temperature process could make the control loop difficult to stabilize. Another assumption we will make is that the downstream temperature transmitter is located close to the heater so that dead time is negligible. Now let's look at the block diagram of the system. We have two processes that operate in series, the steam flow process and the heater process. Each of these has a load disturbance, the steam header pressure for the steam flow process and the feed flow inlet temperature for the heater. The rate of the feed flow, remember, is considered to be constant and therefore is not considered to be a process load. This system has only a single loop feedback control, which monitors the output temperature and transmits it to the temperature controller. This in turn opens or closes the steam valve according to the controller requirements. The problem with this system is that if there is any jump in the steam header pressure, we won't know about it until we see an error in the output temperature coming out of the heater, and there is nothing that we can do about it other than shut down the steam valve. What we are going to do is to implement cascade control by adding an inner control loop for the steam flow process. Since our primary objective is to control outlet temperature, we will call this our primary loop. The output of this temperature controller becomes the remote set point of this flow controller, which actually manipulates the control valve. On the block diagram, we can see that the steam flow loop is the secondary or inner loop. Disturbances in steam header pressure are picked up and fed back to the steam flow controller, which makes a correction before the disturbance can affect the heater process. Now, only the feed flow inlet temperature has a significant effect on the outer or primary loop. Looking at this block diagram, you can see why the inner loop must have a considerably faster time constant than the outer loop, so that it can accomplish its control action before a significant error reaches the second process. Our second example concerns level control. As shown in the illustration, the vessel is drained at a constant rate by this pump. Since the primary objective is to maintain a steady tank level, the main load therefore becomes the inlet flow rate. Since the inlet flow represents a fast developing disturbance to the tank level, there may be significant deviations from the tank level set point as a result of inlet flow changes. In block diagram form, we can see that with single loop control, the level transmitter supplies a feedback signal to the level controller, which in turn opens or closes the inlet flow valve in order to adjust the tank level. The potential problem here is that any disturbance to the inlet pressure will cause an error that will not be detected until it shows up as a change in tank level. Adding cascade control can improve loop performance by having the level controller change the set point of the inlet flow controller. The level controller is the primary loop, and the flow controller becomes the secondary loop. In this way, inlet pressure disturbances are monitored and controlled before they can significantly affect the level of the tank. Remember, for cascade control to be effective, the inner loop must be faster than the outer loop. Also, the outer loop should include a controller with the reset mode in order to eliminate any existing error between set point and actual tank level. In order to protect the process, it may be necessary to limit the amount of set point adjustment on the secondary controller made by the output of the primary controller. This can be accomplished by limiting the maximum and minimum output of the primary controller through the adjustment of the output limiting devices. Because cascade loops are by nature interactive, a specific procedure should be followed for tuning and startup. As indicated on this chart, the proper order of operations is first to tune the secondary loop, beginning with placing the secondary controller in local set point mode and the primary controller in the manual position. Now we tune the secondary controller as a normal feedback single loop. Next, we adjust the primary output or the secondary local set point until they are equal. We then switch the secondary loop controller to remote set point or cascade mode. The set point of the primary controller is then matched to equal the value of the process variable, after which the primary controller is set on automatic and tuned by normal guidelines. One final cascade loop example is positioner cascade control. The control valve, which is connected to a controller output, is the most common of all cascade loops. The controller output adjusts the set point for a valve position. The positioner is a high-gain proportional device whose output causes the control valve to move. The movement of the control valve provides feedback which indicates the actual position of the actuator, which is the process variable, to the positioner. The valve and its positioner, therefore, become the secondary loop in a cascade system. Again, notice that the primary loop must be slow in order to use a positioner. Otherwise, its effectiveness will not be realized. Under normal conditions, there is a set point setting for the secondary controller for each primary variable value. A proper relationship between these two scales is important for good cascade control. The range of the secondary should always overlap the range of the primary, or else control will be lost near the ends of the range. This is noticeable as we look at how the two should relate for a linear process.